Okay, students, now we will see one important topic in the digital communication, matched filter receiver. Now forget about the matched filter, first a receiver. So now you tell me what is the input to the receiver? The input to the receiver is a transmitted signal, is it not? Now the transmitter transmits a signal, that signal is transmitting through a channel and it will coming at the input of the receiver. Okay, now my question is, now this is the receiver, now input to the receiver is a signal, but that signal is all the way traveling through the channel because of the various losses associated with the channel. Now definitely that signal is gets affected by noise, right? The signal is gets affected, the signal is gets distorted due to various losses. So that is nothing but affected by noise. That signal is affected by noise. Therefore, definitely the input to the receiver is a signal which is affected by noise. Okay. So at the receiver input, now what I am using is I just use a filter. Forget about match. Now receiver is clear. Now I just come to the word filter. So at the receiver, I put a filter. For what purpose, sir? Now this filter input is a signal, not only a signal, the signal is added with noise, am I not? Now one of the property of the thermal noise is additive in nature, always added to the signal. So this is noise affected signal, the signal is added with a noise. So this is having some signal to noise ratio, am I not? Signal and some noise ratio. Now this is a filter and this is the filter impulse response and this is the filter output. S0 of t is a filter output. S of t is the input signal to the filter. S of t is the input signal to the filter. S0 of t is the output of the filter. Okay, output signal at the filter output. Okay, signal at the filter output. So now the question is, the purpose of this filter is what? Now why you are using a filter at the receiver side? What is the role of filter in this digital communication? Now see here, this role of filter. Now why we are using a filter? Okay, now this filter is sampled for every TB seconds because this is a digital system, each bit is having a duration of TB seconds. Therefore this signal is sampled over a duration of TB seconds. Now which means that now this is a signal. Now this signal, let us assume, is sampled for TB seconds. Therefore this is S0 of TB, sampled value, am I not? This is the sampled value at the output of filter. Now the question is, here the purpose of filter is when the noise effect is more, right? When the noise, already that is a noise added signal, if the effect of noise is more, then there is a chance of getting the error. Therefore what we are doing is, now here the purpose of filter is to maximize the signal to noise ratio. What happened? The signal filter is to maximize the signal to noise ratio. Here the filter, the purpose of the filter is maximizing the signal to noise ratio. The filter is maximizing the signal to noise ratio such that what happened? Now here the signal to noise ratio is maximum. After maximizing the signal to noise ratio, then that signal is sampled for TB seconds. Now that signal is sampled for TB seconds, S0 of TB, sample value at the output of the filter. Then that will go to the threshold comparator. Now see here, now first the purpose of filter is maximizing the signal to noise ratio. After maximizing that signal, then that signal is going for sample for every TB seconds. Therefore now that sample value, this one, S0 of TB, this sample value is compared with the threshold comparator. Now one of the input to the threshold comparator is sample value and another input to the threshold comparator is the threshold voltage. Am I not? This is the threshold voltage. You know the threshold voltage for a different scheme. Therefore, the sample value is compared with the threshold voltage. Let us take for example, now this is threshold comparator. Now this is S0 of TB. Now this is threshold voltage. Now, if this sample value is greater than the threshold voltage, now the output of the threshold comparator is treated as binary 1. If this sample value is less than the threshold voltage, then the output of the comparator will be treated as binary 0. The threshold voltage is more than the sample value is more than binary 1, less than binary 0. Now this is the way generally the threshold comparator will take a decision. So now what happens here, if effect of noise is more, binary 1 will be treated as binary 0, binary 0 will be treated as binary 1. Now what happens? If effect of noise is more, errors will occur. Am I not? So what we want? We want the error should be probability of error, or error should be as minimum as possible. But this type of errors should be as minimum as possible. So the probability of error should be as minimum as possible. So to get the minimum error probability, see here, to get the minimum error reverse, I'll go to the reverse. To get the minimum error probability, now the effect of noise should be less. But that is not in our hand. The noise effect, we cannot be negligible. That will be added, that will be coming. So if this probability of error should be as minimum as possible, then the signal strength should be as maximum as possible. Okay, the signal strength should be as maximum as possible. So that is the reason why, to maximize that signal strength or to maximize that signal to noise ratio, then we use the filters at the receiver side. Now this is the filter receiver, but why the name is coming as matched, that we will see characteristics of the filter. Okay, so the word is matched. The reason behind the match, that we will see, but this is the purpose of the filter. That's why I'm not using a rule of match filter. I'm using a rule of filter. What is the use of filter? Why the filter is used? For what purpose the filter is used in the receiver at the input side? Okay, now this is the purpose of the filter for utilizing in the receiver's topic. But why that filter named as a matched filter, we will see with the derivation part, with the theory part. Okay, now first you note on this. Now is it clear or not? Now see here. So to fulfill this particular features, now how that filter specifications, how the filter is working, now what type of characteristics the filter should have, such that we'll get this type of advantage. Okay, now we'll see the designing part of the filter, and we will see the signal to noise ratio maximum, how it will be maximizing the signal to noise ratio, and what should be the characteristics and everything we will see. Okay, right. Now before that, you just take everything. Okay. Now you tell me, now what is S0 of t? S0 of t, which is nothing but convolution of S of t and H of t. Now this is a convolution in time domain, then which is nothing but multiplication in frequency domain, S of f multiplied with H of f. Okay. Now see here, Now we'll go one by one. Now first we'll see S naught of t, output of the filter. S naught of t, which is inverse Fourier transform of S naught of f. Is it right or not? Yes. So what is that? S naught of t, which is equal to integral minus infinity to infinity S naught of f e power plus j 2 pi f e power plus j 2 pi f e power plus j 2 pi f t df. Now S naught of t, which is equal to integral minus infinity to infinity. What is S naught of f? S naught of f, which is nothing but S of f into h of f e power plus j 2 pi ft df. So can I write like this? This is S naught of t, but this signal is sampled for tb seconds. Therefore S naught of tb, which is equal to integral minus infinity to infinity S of f h of f e power plus j 2 pi f tb df. But I want to maximize this, am I not? Now signal power at the input of comparator, threshold comparator, input of comparator is for maximizing. Okay, now this is a power square energy S naught of tb whole square, because I want to maximize in the signal, right? Signal to noise ratio should be maximum, means the noise we cannot do anything, but we can maximize the signal strength. So this is the maximizing the value of signal. For maximizing, I just do this square it, because the energy maximum value. Therefore S naught of tb. So this is the signal strength. Now this is the signal power. Signal power I represented with S, which is equal to S naught of tb whole square, which is equal to integral minus infinity to infinity S of f into h of f into e power plus j 2 pi f tb df. Whole square. Okay. Now there is a property called as Schwarz inequality principle. Now the Schwarz inequality principles saying that integral minus infinity to infinity f1 of t f2 of t dt whole square, which is less than or equal to integral minus infinity to infinity f1 of t whole square dt into what the Schwarz inequality principle is saying, integral minus infinity to infinity f1 of t into f2 of t dt whole square, which is less than or equal to integral minus infinity to infinity f1 of t whole square dt integral f2 of t whole square dt. Now this is possible only when f2 of t and f1 of t are complex conjugate to each other. Okay, this is complex conjugate to each other. So can I apply this one? Now can I apply this one? Therefore the signal power, which is nothing but integral minus infinity to infinity mod s of f whole square df integral minus infinity to infinity mod h of f whole square df, because modulus of e power plus j 2 pi f tb value is how much? 1, because mod of e power ix is nothing but cos x plus I sin x. Now square root of cos square plus theta plus sin square theta, which is nothing but mod of e power ix, which is equal to mod of cos x plus I sin x, which is equal to 1, because square root of cos square theta plus sin square theta, real part square plus imaginary part square, so whose value which is equal to 1. Therefore that's why this is equal to 1. And this splitting is possible only when these two signals are complex conjugate. Now let us see, for example, this is h of f, which is equal to s of f into e power plus j 2 pi f tb whole complex conjugate. Now because he says that f2 which is equal to f1 complex conjugate, this is possible, then only the splitting is possible. Okay, this splitting is valid when f1 f2 are complex conjugate, whether this one is complex conjugate of this or this one is complex conjugate of this. Okay, now this is for signal portion. Okay, this is for signal strength, and up to this is the signal strength output of the filter, but I am maximizing because I want the maximum signal to noise ratio. Therefore for maximizing I then take the square root, because the energy of the signal is the maximum value. Okay, now this is the signal portion. Now we will see what is the noise portion later. First you note down this. Okay, now this is about the signal strength. Then we will see the noise power at the output of the filter. Now see here, now this is the filter. Now this is the filter. Now this is the impulse response of the filter. Now this is a noise power spectral density. Now this is a power spectral density of noise, which is input to the filter, right? Now, but this is, we want filter output. This is filter output. Now what is the power spectral density at the output of the filter? There is a relation. When a power spectral density is at an input to the filter and filter is having a transfunction, so power spectral density at the output of the filter, which is nothing but power spectral density at the input of the filter, power spectral density at the input of the filter multiplied with square of the filter transfer function. You know, okay, this is the relation of power spectral density, effect of noise and filter transfer function. A power spectral density at the output of the filter equal to power spectral density at the input of the filter multiplied with square of the filter transfer function. Now What is the power spectral density? This is the power spectral density at the output of the filter, which is equal to, what is the power spectral density at the input of the filter? Is nothing but a noise. What is a noise? Thermal noise. What is the thermal noise power spectral density? Now, additive white Gaussian noise, whose power spectral density is uniform, right? N naught by 2 into a square of the filter transfer function. But I am not interested on the power spectral density at the output. I want a power spectral, I want a noise power. But this is a power spectral density at the output of the filter. So this is nothing but noise power spectral density. Am I not? This is noise power spectral density at the input side. This is noise power spectral density at the output side. Therefore, this is power spectral density of noise at the output of the filter. But I want a noise power. There is a relation. Now, what is a noise power? This is a noise power represented by capital N. The area under power spectral density, area under noise power spectral density, area under noise power spectral density is nothing but a noise power. Area under noise power spectral density. Therefore, which is equal to N naught by 2 is integration minus infinity to infinity. Now, this is h of f square df. This is the noise power. Okay, note down. Now, this is the noise power at the output of the filter. This is the signal power at the output of the filter. But what we want now, the role of filter is producing a maximum signal to noise ratio. Now, what is the maximum signal to noise ratio? This is the noise power. This is the signal power. Now you find what is the signal to noise ratio. Now this is the signal to noise ratio. Now this signal to noise ratio is integral minus infinity to infinity s of f whole square integral minus infinity to infinity h of f whole square df. Now the noise power is n naught by 2 integral minus infinity to infinity h of f whole square df. This is cancelled. Therefore, signal to noise ratio, which is equal to integral minus infinity to infinity s of f whole square df by, now this is n naught by 2. Now this is the signal to, this is actually less than or equal to, right? Not, because this is a Schwarz inequality principle, then we can split the integration. This is less than or equal to. Now see here, now this is the signal power and this is the noise power and this is the signal to noise ratio at the output of the filter. Now see here, now I am asking about what is the maximum signal to noise ratio. Now for getting maximum value, you tell me. Now this is the signal to noise ratio, but what is the maximum signal to noise ratio? So when I am asking question, signal to noise ratio maximum, which is nothing but this is less than or equal to, so maximum value means equal. Now this is nothing but integral minus infinity to infinity s of f whole square df by n naught by 2. Now this is nothing but, what is this n naught by 2? A noise power at the input of the filter, and this is the energy spectral density. This is energy, am I not? S of t whole square dt is nothing but energy of the signal, but this is in frequency domain. Therefore, energy spectral density. Energy spectral density of the signal. Energy spectral density of signal S of f, energy spectral density of signal, S of t, energy, but this is a spectrum, means in frequency domain, by what is n0 by 2, power spectral density of noise at the input of the filter, at the input of the filter. So power spectral density of noise at the input of the filter will be same as the power spectral density of noise at the output of the filter, means the noise effect will be same. But what happened? Now this is energy, signal is maximizing, so energy of the signal, so this is the maximum value, then this is the overall signal to noise ratio maximum. Hold on. Okay, so now this is S of t, now which is nothing but this is S of t, this is nothing but energy of the signal, right? Now this is S of f, now this is nothing but what is this, right? Now that is energy in time domain, this is energy in frequency domain, power versus frequency, power spectral density, right? Magnitude versus frequency, magnitude spectrum, energy versus frequency, this is nothing but energy spectral density. This is the energy spectral density, units are joules per hertz. Spectrum means frequency, energy means joules. But now what is here? Now this is S of f whole square. This is nothing but energy spectral density, joules per hertz. But now this is multiplied with df. What is df? df is nothing but frequency, hertz. What happened? Hertz cancel. Now which is nothing but joules is nothing but what is this? This is nothing but joules, which is nothing but energy of the signal. Energy of the signal. So finally, now this is nothing but the signal to noise ratio maximum is nothing but energy of the signal, energy of the given signal, energy of the given signal by power spectral density of noise, thermal noise at the input of the filter, or everything will be same. So can I write like this? This is nothing but energy of the signal ES by noise power spectral density of thermal noise. Okay, now this is the signal to noise ratio maximum value, which is output of the filter. Now what is the condition? Now this signal to noise ratio maximum value, this is valid, am I not? Now this is true with a condition, am I not? Applicable when this condition is satisfied, am I not? Now this splitting and everything is possible. So this is the signal to noise ratio maximum value is produced by the filter. Now my question is, to get this maximum signal to noise ratio, how this filter characteristics? Okay, now here I get a maximum signal to noise ratio. I get signal to noise ratio value is maximum, such that how this filter specification to get this maximum signal to noise ratio, now how this filter characteristics or filter impulse response is designed. What is the filter's impulse response? Now you already know, if this is the maximum value, h of f, which is equal to this one, s of f into e power plus j 2 pi f tb whole complex conjugate, which is nothing but s complex conjugate of f into e power minus j 2 pi f tb. Therefore, which is nothing but, what is h of t? H of t, which is equal to, see here, h of t, which is inverse Fourier transform of h of t, which is inverse Fourier transform of h of f. H of t, which is equal to integral minus infinity to infinity h of f into e power plus j 2 pi f t df. Now you can substitute here integral minus infinity to infinity. What is h of f? This is h of f. H of f is s complex conjugate of f e power minus j 2 pi f tb. Now this is e power plus j 2 pi f t df. Now can I write like this, which is nothing but integral minus infinity to infinity s complex conjugate of f into e power, will take minus j 2 pi f as a common, e power take minus j 2 pi f as a common, tb minus t. df. So can I write like this, integral minus infinity to infinity s of f, I remove this complex conjugate, plus j 2 pi f tb minus t df. Now this is whole complex conjugate. So now what is h of t? See here, now h of f, this is integrate with df, but this is t actually, therefore that is s of t. But what is here? Now h of t, which is nothing but s of tb minus t complex conjugate. If assume signal s of t is a real value, real function, real one, then no complex conjugate is required. S of t, which is equal to s of tb minus t. Now this is the impulse response of the filter. So if you observe or not, this impulse response of the filter, it should be the impulse response of the filter, now whose operation is in terms of input signal to the filter, am I not? The impulse response of the filter whose operation is in terms of the signal operation itself. Now whatever a signal, that should be that operation which is time inversion and just shifted to the right side of a given signal. Okay, then sir, why this filter named is match filter, that we don't know. Okay, now we will see. But now so far what we know is, we know what is the receiver, you know what is input to the receiver. So input to the receiver, why you are using this filter, what is the role of the filter, and what is the filter characteristics, how signal to noise ratio is maximum, what is the maximum signal to noise ratio at the output of the filter, what is the filter characteristics, and everything is clear. Now we will see the reason behind why this filter is said to be matched filter, why this filter is named as matched filter. Now we will see. Now first you take this is the impulse response of the filter. Okay. Now why this filter is named as matched filter, we'll see. Now finally, what is the impulse response of the filter? The impulse response of the filter, which is nothing but S of TB minus T. Now first we'll see one small question such that you can easily understand. Now this is the input signal to the filter. Okay, see here, rectangular pulse. This is a input signal to the filter. Now asking to find impulse response. Okay, this is the input signal to the filter and asking to find impulse response. For finding the impulse response of the filter, there are two steps. Okay, now first step one is first you fold the signals S of minus T, folding, right, inversion, fold the signal. Okay, just fold the signal. Let us assume this is A, amplitude is A. Okay, this is the step one of any signal. These are the steps you fold for finding the impulse response. Now first you, whatever the signal is given, you fold it. Okay, that is step one. Now step two is, step one is folding. Step two, shifted to right side. After folding that signal, you just shifted to right side. Shifted to right side. Now you just shift to the right side. Push it. Shifted to right side. The first step one is folding and shifted to right side. Now if you do these two operations, this is step two, shifted to right side. If you do these two operations, now that will be the impulse response of the filter. Okay, now step one is folding, step two is shifted to right side, then that will be the impulse response of the filter. Now you see here, this is the impulse response of the filter. Now students, you concentrate here. This is the impulse response of the filter. Now see here, this impulse response of the filter is matched with, see here, now this is the impulse response of the filter. This impulse response of the filter is matched with input signal or not? Now this is the input signal to the filter. This is the input signal to the filter. The impulse response of the filter is matched with input signal. Therefore, this filter is named as matched filter. Clear or not? Listen carefully. The impulse response of the filter, you see here, the impulse response of the filter is matched with the input signal, then this filter is said to be matched filter. Okay. Now whatever the impulse response of the filter will be same as that of the input signal, then that filter is said to be matched filter. Now if any filter whose impulse response will be same as that of the given input signal, now definitely that filter will produce a maximum signal to noise ratio such that now here the error probability should be, minimum. When the signal to noise ratio is maximum, now here now the error probability should be minimum. The probability of error should be minimum. You can get a minimum error probability when maximum signal to noise ratio is happening here. Okay, so this will get the maximum signal to noise ratio. Now the filter is producing a maximum signal to noise ratio. The filter should have a characteristics of the impulse response of a filter should be a function of the input signal, or sometimes it will be same as that of the input signal. The impulse response is matched with the input signal. Therefore, this filter is named as, therefore, the impulse response is matched to the input signal. The impulse response is matched to the input signal. Therefore, the filter is said to be, matched filter. The filter is said to be matched filter. Okay, the impulse response of filter is same as the input signal or matched to the input signal. Therefore, the filter is said to be matched filter. Now, this is the reason why this is matched filter, and which is used at the receiver in the digital communication to get maximizing the signal to noise ratio and to get a minimum error probability of ones and zeros having less error. Okay, not. Okay, now see here. Now this is the impulse response of the filter will be same as that of the input signal. Therefore, this filter is named as matched filter. Now my question is, this is h of t. This is h of t, which is the impulse response of the filter. Now I want output of the filter. Okay, what I want? Now I want output of the filter. Now what is output of the filter? Now the output of the filter, which is nothing but S naught of t, which is equal to S of t convolved with h of t. What is S of t? S of t, which is nothing but a rectangular pulse of pulse width Tb, pulse height or amplitude is A. Now this is convolution of h of t. The impulse response of the filter is same as that of the input signal. Now what is the output? Now the convolution of the two rectangular pulses. What is the convolution of the two rectangular pulses? The convolution of the two rectangular pulses is nothing but a triangle or not? A convolution of the two rectangular pulses is a triangle, but whose duration is doubled. Maybe you know this is very famous in signals and system topic. Convolution of two rectangular pulses. Now this is output of the filter. This is output of the filter. Clear or not? Now this is the output of the filter. Now if you observe or not, so now finally Now this is the output of the filter is sampled for every TB seconds, am I not? Is sampled for every TB seconds, which means that, now see here, what is S naught of T? Now S naught of TB, the sample value. Now this is the sample value at the output of the filter is going for a decision for a threshold comparator S naught of TB, which is equal to A square TB. This is for, this is a rectangular pulse. What is a rectangular pulse? Is a binary one. This is for binary one. A square TB for binary one. Now S naught of TB equal to 0 for binary 0, because this is which representation? On off representation, because in on off representation binary 1 means positive voltage, binary 0 means 0 volts. Okay, this is a on off signaling. Now if it is a, now you tell me, if it is a non return to 0 signaling scheme, if it is a non return to 0 signaling scheme, now you tell me S naught of TB, which is equal to A square TB. S naught of TB, which is equal to A square TB for binary 1, and which is equal to minus A square TB for binary 0. Now this is for non-return to 0 scheme. Note down.